Hi guys, this is Miss Hargrave, and we are going to do a little bit different kind of presentation than we're used to. So here's my face. Hi guys. And I'm going to start with some questions for you guys that I want you to think about. Then we're going to do a little activity and go over a few of our first gas laws. So I want you guys to test some of your knowledge from chapter 13. How can you describe gas pressure? I'm going to give you a minute to think about it. Okay, hopefully you came up with something along the lines of this. Gas pressure is the result of collisions of particles within their container. Okay, so if that is true, how does increasing the number of particles in the gas affect the pressure? Again, take another minute, think about it. Hopefully you got your answer. Alright, the more particles colliding within the walls of a container, they're going to increase our pressure. Okay, so the more particles, the more pressure. So, I have a visual for you guys. Alright, so I have these two containers, okay, and they are the exact same size. Okay, both of them are 250 milliliter beakers, okay, and you can tell the particles inside, okay, are the same number, just different sizes, and I'll show you a picture of those, okay. In one side, they're different colors, but they're this big, okay, sorry guys, this is all I've got, and in the other one, particles are just this size. Okay, so inside their beakers, same number of particles. Okay, let's imagine that these plastic pieces are gas particles. Okay, which one of these containers will have more pressure? Okay, think about it, and we'll come back to it. Okay, so here's our beakers again, and you've thought about it a little bit, hopefully. So in these containers, okay, we have our gas particles. I want you guys to assume that these are closed containers, okay, not open. So pretend they're closed. And that the temperature is the same for both containers, okay. I want you to compare the pressures of these two containers. Which one would have a greater pressure? Which one would have a lesser pressure? Is it going to be orange beads or are little yellow gray bead things? Okay, take a second, think about it. Which one has more pressure? Hopefully, as you thought about it and analyzed the information that you guys have read so far, you would say that the pressures are the same. Okay, and the reason for that is that are identical pressures because each container holds the same number of particles of gas. Okay, I counted them out. They're exactly the same. Okay, just different sizes. So the average kinetic energy is still the same for our volume. Okay, in the same volume. Okay. All right. Let's move on. Alright guys, here we go. So we're going to talk about Boyle's Law first, since it's the first one in our 14.2 over gas laws. With Boyle's Law, it says if T is for temperature, is constant and pressure is increasing of our gas, okay, then our volume will decrease. So these are inversely related. And you can see I have our formula up for us. Alright, so you've got the first pressure and the first volume, okay, they're going to be equal, should be equal to the pressure and volume of our second reading. Okay, so let's go ahead and do an example. Alright, so here is our example, and I put our page number up. We're on page 419, okay, so you can follow along in our example. So you are given a helium-filled balloon, and I just put HE for the symbol, but that looks weird. Okay, so helium. Helium-filled balloon. Alright, and it is told to you that this balloon has a 30-liter volume, okay, at 103 kilopascals, which is its pressure. Okay? So these are initial readings. Then the question says, what if, or what is the volume of our balloon if it rises to an atmospheric pressure of 25 kilopascals? So you want to figure out what are your initial pressures and volumes, and then what are your secondary or the end results that you want. So we're told that we start with 30 liters, okay, and that's the volume pressure, and kilopascals is pressure. So here's our 103 ppm, and then our first volume is 30 liters, okay. Then it says if it rises to this pressure, okay, so that would be our P2, 25 kPa. So what we're trying to find is our volume 2. So with our formula over here, and I will twist this just a little bit more, hopefully you can see it, we need to isolate this one. Okay, so if we divide by P2 on both sides, then we will get what V2 equals. So V2 will equal P1 over V1 V2. Okay, so then plug in your information. So for P1 we have 1 over 3, and that's kPa. And then it's going to be multiplied by our first volume, 30 liters, close to the edge, over 25 kPa. Our kilopascals cancel out, and we're going to have V2, which is in liters. Okay, so let's see our handy dandy calculator. Okay, you've got 103 times 30 divided by 25, and you should get 123.6 meters. Okay, so our balloon will increase in size, and hopefully that's a good example.
Gas. It's all around you. It's in space. It's on Mars. It's dissolved in your blood and in your soda. It's everywhere. And it's easy to forget that we're submerged in an ocean of gas, but it's there all the time. You can feel it if you wave your arms around. You can't look cool while you're feeling it, but you can feel it. It's there, those little molecules and atoms bumping around against your hand as you wave them around. Feel it? Are you doing this? I've got good news and bad news about gases. First, the good news, when they're behaving themselves, it is extremely easy to describe their behavior theoretically, experimentally, and mathematically. The bad news is, they almost never behave themselves. The first mathematical description of the behavior of a gas was a link between pressure and volume. In a closed system, like the inside of this balloon, when we decrease the volume of the balloon, the pressure inside goes up. And if we could somehow expand the balloon, then the pressure inside the balloon would go down. If I keep pushing on it, the pressure inside might go so high that it'll break. I can't do it. It's a very strong balloon. The relationship here is a simple one. When you multiply the pressure and the volume together, you get a constant. As long as the temperature and the amount of gas stays the same, so does that constant. It's called Boyle's Law, and it was a pretty big deal back in the 1600s. It's also one of the greatest scientific misattributions of all time. Robert Boyle was a super rich Englishman raised in Ireland. His father was so rich that he paid another family to raise his children. I guess because he was too busy administering lands or something. Boyle had lots of great ideas about science and chemistry, his most important one, and this is arguably even more important than Boyle's Law, being that chemists should publish papers not on what they feel is correct, but rather on theories that have been backed up by experimentation. Richard Townley, a wealthy but considerably less wealthy Englishman, struck up a relationship with Boyle, telling him about some of his work that would disprove one of those but it feels right kind of chemists. Boyle published a paper mentioning that work, which he called Townley's hypothesis, but which ended up, because of Boyle's superior scientific standing and possibly his wealth, being called Boyle's Law. But here's the really messed up thing. The experiments that led to the creation of this theory were actually done largely by Townley's family friend and physician, Henry Power, who's not a member of the aristocracy at all. He was just a working class scientist. Power was working on a publication that would have snared him the position as discoverer of the relationship between the pressure and volume of a gas, but Boyle, having discussed the ideas with Townley privately, published his first, attributing Townley as the sole researcher, ensuring that Power's contributions were all but lost to history. Henry Power's Wikipedia page didn't even mention Boyle's law until a few weeks ago, when I personally added a paragraph about it, with proper citations, of course. But no matter who thought it up or who it got named after, Boyle's law is pretty cool. For a given amount of gas at a constant temperature, pressure times volume always equals the same number. But where is that constant coming from, and why is it different for different amounts of gas at different temperatures? Well, it was more than 100 years before we'd figure out the answers to those questions with the help of a Frenchman, Jacques Charles, and our old Italian house elf friend Amedeo Avogadro. Charles and Avogadro created equations much like Boyle's law, with two features of a gas being linked directly together by constants. Charles discovered that volume divided by temperature equals a constant, as long as the pressure remains the same, and then Avogadro figured out that volume divided by the number of moles in the container at a constant pressure and temperature gave yet another constant. But here's the crazy cool thing: all of these scientists were basically dealing with a different form of the same equation. An equation that we must never forget, and is gonna be stuck in my head until I die. And here's how it works. Pressure times volume is equal to the number of moles of substance times a constant times temperature. PV equals nRT, the ideal gas law, which works for all gases as long as they behave themselves. Now here's the cool part. Using this equation, we can show how all of these chemists were dealing with the same relationship. They were just clumping various variables together in different orders. All of the chemists we just mentioned, Charles, Avogadro, and Boyle, or more properly Townley and Power, figured out their contribution to the ideal gas law experimentally. But more interesting to me is that it can be understood theoretically. First, we have to understand what each of these variables actually mean. In that same way, the atoms and molecules that make up gases are bouncing against things, applying pressure to them. This balloon is inflated because the molecules are bouncing around inside of it, bumping into the inside of the balloon harder than the molecules bouncing off the outside of the balloon. Scientists generally measure pressure with the SI units of force, newtons per area, meters squared, which is shortened to pascals. But since pascals are so tiny, we either use kilopascals or we use the pressure here on Earth at sea level that we call 1 atmosphere or 1 ATM. Completely by chance, 1 atmosphere is equal to 101,325 pascals, but that's so close that we often just say that 1 atmosphere is 100,000 pascals or 100 kilopascals. Volume is the amount of space particles have to exist inside of, so yeah, that makes sense. When the volume goes down, the pressure goes up because there are more particles in a smaller space and they'll each hit the walls more often. N is simply the amount of gas, the number of moles in the system. Here I am decreasing the amount of gas in the system, and in response the volume is decreasing, obviously, but so is the pressure inside the balloon. R in the ideal gas law is called the universal gas constant, even though, as we will see in a coming episode, it is neither universal nor constant. It's 8.3145 liter kilopascal per Kelvin mole. Temperature is experienced by you and me as hot or cold, but at the atomic level it's kinetic energy, literally how fast or slow the average particle is moving. So if temperature goes up, so will the pressure, as the particles are moving faster, and thus will run into the sides of the container more often. So now we know about all of the little bits of the ideal gas law, so let's take a look at it in action. We here at Crash Course generally like to be very safe. This is a little bit overkill here. I put a little bit of water into this soda can, and now I'm boiling it. So instead of atmospheric gas in this can right now, there's water vapor, and it's hot, and all the molecules are zipping around like crazy. We pick it up, and we plop it down inside of that. Oh, and it crushes itself. So what just happened there? Well, let's see what the gas law can tell us. So which of these things are changing? Starting on the right-hand side, R is constant, so that can't change. The temperature of the gas, though, that definitely changes. It drops like mad when it's exposed to the ice water. N is decreasing too, as water vapor is condensing into liquid water. It thus disappears from the gas phase, so the net result on the right-hand side is a decrease, and that means the left-hand side has to have a net decrease too. So on to the left-hand side. The pressure does indeed drop because the lower temperature makes the molecules move more slowly, thus bumping into the sides of the can a lot less than before. And volume drops too, but not quite for the reason you might think. It's really that the pressure inside the can goes so low that the pressure outside the can, the atmospheric pressure, literally crushes the can. Now I understand that you probably don't think this is as cool as I do, but understanding the physical reality of atoms and molecules smacking into things is a special kind of beautiful for me. It's also pretty cool that if you know any 3 things about a gas, you can figure out the 4th using the ideal gas law. Of course, not all gases behave ideally, and all gases deviate from the law at low temperatures or high pressures, but we'll save that discussion for a later episode. Jargon fun time! STP means standard temperature and pressure, which according to the lords of chemistry is 0 degrees Celsius and 100,000 pascals, or 100 kilopascals. 1 mole of any ideal gas takes up 22.4 liters of space at STP, which is a fact that can simplify a lot of calculations. Absolute zero is the temperature at which all movement of all particles stops. It is 0 kelvins, or negative 273.15 degrees Celsius. And that's all for this episode. Thank you for watching Crash Course Chemistry. If you were paying attention, you learned about how the work of some amazing thinkers combined to produce the ideal gas law, how none of those people were Robert Boyle, and how the ideal gas equation allows you to find out pressure, volume, temperature, or number of moles as long as you know 3 of those 4 things. And you learned a few jargony phrases to help you sound like you know what you're talking about. This episode of Crash Course Chemistry was written by me, the script was edited by Blake DiPastino, and our chemistry consultants were Dr. Heiko Langner and Edie Gonzalez. It was filmed, edited, and directed by Nicholas Jenkins. Our script supervisor was Caitlin Hoffmeister, and our sound designer is Michael Aranda. Our graphics team is Thought Cafe.
Okay, so here are a lot of the gas equations we've talked about. Who wants to memorize them all? I don't. You might think you have to memorize all these, and maybe your teacher has even asked you to do that, but you don't have to, because I'm going to show you an incredibly useful trick in this video so that you will never have to worry about memorizing all these guys. Here's how it works. All you have to remember is the ideal gas law. PV equals nRT. And it kind of has a nice ring to it, so it's really easy to stick in your mind. You remember PV equals nRT, and you can use it to get any of these other gas laws whenever you need them to solve a problem. So we can put all these guys away because we don't need any of them anymore, and I'll show you how to use PV equals nRT for this trick. So let's say that you're given a problem like this, okay? We have a before and after, we have pressure and temperature are both changing. So we look at the variables we're dealing with, as I just said, pressure and temperature. And what I want to do is I want to take PV equals nRT, the ideal gas law, and rearrange it so that the variables I'm interested in, pressure and temperature, are by themselves on one side of the equation. Doesn't matter which side it is, okay? So pressure and temperature. So to get P and T by themselves, I'll first divide both sides by V here. And then V over V will cancel out. So now I have P equals nRT divided by V. And I want to get T on the other side of the equation so it can join P. So I'll divide both sides by T. And now T over T cancels out, and I'm left with PT, P over T, equals NR over V. Okay, so we have P over T on one side of the equation. Now, it turns out that if something is on one side of the ideal gas equation, you can double it on the other side, doing a before and after thing. Here's what I mean. We can take this P over T and turn that into P1 over T1, there's a before, and then we double it on the other side, equals P2 over T2. What we've actually just done is we've created Gay-Lussac's law. But I didn't have to memorize it, and all I had to do is take PV equals nRT and figure it out from there. Okay, let's look at another example. Here is one where I have an initial pressure, a final pressure, initial volume, and final volume. So the variables that I'm interested in are pressure and volume. As before, I want to rearrange the equation so that I have pressure and volume by themselves on one side. That was easy. The ideal gas law is already written so pressure and volume are by themselves on one side. Okay? So what we do now is we double this PV on both sides of the equation, doing before and after. So P1 times V1 equals, double it on the other side, P2 times V2. And now I can plug in my variables and solve for V1. And check it out. What I did was I used PV equals nRT, to come up with Boyle's law. Okay, you're probably getting the hang of it. I'm going to do two more examples, but if this already makes sense, go ahead and move on. Now, one question that I do often get is, how do you know which variables you want to rearrange the equation for? You know, teachers and textbooks don't always ask questions where they just say V1 is this, N1 is this, and so forth. So if you're given a word problem, it can be a little bit trickier to find out what variables you're using and whether they're V1, N2, or whatever. So if you're having a little trouble figuring out what the variables are, watch my video called Which Gas Equation Do I Use? And that will tell you how to read a word problem and figure out which of the variables you're working with, okay? So this one, we're going to be using volume and moles. So we want to rearrange the ideal gas law so that I have volume and moles by themselves on one side, okay? I will get rid of P so that I have only V alone on this side. Divide both sides by P. And then I have V equals nRT divided by P. And I want to get N to the other side, so I'll divide both sides by N here. Cross that out. And then I have V over N equals RT over P. I have this guy by itself, so let me double it before and after on both sides of the equal sign. V1 over N1 equals V2 over N2. And what I did there was I came up with Avogadro's law. One more. This is for one that's a little bit trickier. I have a before and after here where three variables are changing. I have volume, pressure, and temperature. So everything that I've been doing up until this point has just had two variables changing, but it's no big deal. You can use this technique for any number of variables. So volume, pressure, and temperature I want to get on one side of the ideal gas equation. So I already have pressure and volume here. So how about I divide both sides by T to get them all together here. Cancel this out. And I'm rewriting it, but it really doesn't matter what's on the right side here. All that matters is what's on the left side here when we get these together. So I now turn this to P1 times V1 over T1, double it on the other side, equals P2 times V2 over T2. And that was the, where is it here? That was the combined gas law, but hey, I didn't have to memorize it. So that is how you can use this technique to come up with any of the gas equations you need and not have to worry about memorizing. But you will have to be able to read a word problem and figure out which of the variables you're working with. So again, if you're having trouble with that, watch that video that I talked about earlier and you should be all set.